All right, so we start part 2 of the course by talking about symmetries. And I drew this triangle, which is schematically something for you guys to have in mind. It's a connection between differentiable symmetries, conserved charges, and representations of Lie groups and Lie algebras. So the connection between differential symmetries and conserved charges, we saw that in the context of the Noether's first theorem. Then last time we started talking about differentiable symmetries, but we didn't really, we started talking about differentiable symmetries and representations, but we didn't really get to connect it to physics. So today I'll start with that, the so-called Wigner theorem. And then eventually we'll come back and find the connection between here and as well. Can anyone guess actually a priori what is the connection here? Anyone? Does anyone know? All right. Well, we'll talk about it. Is the idea of this? It's just to organize everything we're going to talk about in the discussion of symmetries better. Questions? Thoughts? All right. So we'll see how far we get today. We talked about symmetries acting as a group. The action of the symmetries on anything, whatever the symmetry is acting on, forms a group. And we talked about a representation as a realization of the group in terms of matrices, where where group multiplication operation is mapped to matrix multiplication. Inversion, the group is mapped to matrix inversion. What was the other property of the group? Identity. Identity is represented by identity matrix. All right, good. Those are, I mean, technically what I'm talking about is finite dimensional representations, but it doesn't matter for now. How would I change this to make it infinite dimensional? Just replace the word matrix by an operator, right? What is the analog of multiplication for operators? Composition. Composition. All right. We talked about Noether's theorem in the past, which was about the continuous, really not really continuous, differentiable symmetry groups, Lie groups. This is a colloquial definition. I did not define it. And then we said infinitesimal group transformations for Lie groups form a Lie algebra. This is to be understood as the tangent space of the manifold that represents the group. Examples that we talked about are UN. This is the n by n unitary matrices, the group of n by it's a Lie group of n by n unitary matrices. ON, orthogonal n by n matrices. OD, comma 1, orthogonal matrix, not orthogonal. The set of matrices that preserve this metric or bilinear. Of course, we talked about SO of all of these, SON, SUN, and SOD, comma 1. These are the ones that, what was the S? Determinant 1. And you already saw a case where you had two disconnected Lie groups with two disconnected parts, right? All right. What was that? What was the example of two disconnected things? ON, right? Because ON transformations cannot flip this. There are two parts. There's a part that determinant is +1 and determinant is -1, and you cannot continuously transform. This is a super important example. It has dramatic physics consequences. All right, I talked about classification last time very colloquially. Now, I'm just going to make a statement. If we do get to the end of this lecture or the next lecture, hopefully this comment regarding classification will make sense. So I just said Lie groups and Lie algebras are classified. Not really, but for all practical purposes, for physicist purposes, they are. So here's the statement, which is rigorous. All simple, to be defined, what is a simple Lie group? all simple Lie groups are classified. Okay, so this is the true statement. They are the building blocks of Lie groups. So in mathematics, classification problems are that you want to classify some concept, you find the building blocks, and you come up with a method of composing those building blocks to construct more complicated objects. And then you prove an arbitrary object could be decomposed this way. Example, anyone has any examples of this in math? Prime numbers, right? Any positive integer, you could write it in terms of multiplication of prime numbers, right? So they're the building blocks. All right, so here's the same thing. So simple Lie algebras, the simple Lie groups are going to be the building blocks, and that's what we're going to focus a lot on. So what is this reconstruction result? Any finite dimensional and a connected Lie group could be constructed from simple Lie algebras using a method of composition called group extensions. So I'm not here to teach math, but group extension is something to just keep the words in mind. We'll talk about a very special case of group extension called central extension. It's the simplest case possible. Well, not the simplest case possible. It's a simple case, and that plays a role in physics. All right, that's what we're going to be talking about. That's why I said. But in general, there's such a thing called group extension. And the idea is that if you just take these simple Lie algebras that we'll define and classify, well, we'll not classify them, but they have been classified, and you just compose them using group extensions, you get everything, as long as it's connected and finite dimensional. The disconnected part is sort of trivial, right? If it has a bunch of disconnected pieces, just add the connected pieces. The finite dimensional is very important. Infinite dimensional Lie groups they're wacky. They're just way too complicated. So we'll not be dealing with anything like that in physics. Hopefully this we'll come back to this at the end of this lecture if we make it far. All right. So this is just a big thing to along the way in this course, sometimes I make statements that are physicists correct, not mathematician correct, right? And sometimes I do that intentionally, sometimes I do that not intentionally, just because I don't know the story well, but I'm just repeating a sort of bedtime story physicists tell themselves. In this case, it is important that you know what the story is because it plays a role in physics. More complicated examples play a role in physics. So now what we're going to talk about is the connection between these differentiable symmetry transformations and representations of Lie groups and Lie algebras. So what was a representation? It was a vector space where the group elements were acting as matrices, aka otherwise known as linear transformations, right? So it's a linear action of matrices on a linear vector space. What if you take your linear vector space to be the Hilbert space? So this is the only comment I'll make for physics, for quantum. You could always talk about that, right? You have a symmetry transformation. You could ask how your symmetry transformation is represented on the Hilbert space. You know, like the representation theory doesn't give a damn about what your vector space is, right? It could be a set of phi 1, phi 2, a collection of fields that you just put together as a vector, is a linear vector space, or it could be Hilbert space, right? So now we're asking a particular question. If we have a symmetry and you pick your representation vector space to be the Hilbert space, how should the symmetry act? What kind of representation do we need? Let me just give it to you before just elaborating more. Wigner's theorem says that if you are talking about the action or representation of a symmetry on a Hilbert space, it must be either unitary or anti-unitary. Not any matrix, either unitary matrices or anti-unitary matrices. We'll prove that. Well, actually, it's a one-liner, three-liners. So why is that? Why is that? It should preserve the inner product, right? So take two kets, ket and bra, phi and psi, actually two kets, and then whatever the hell that transformation is, representation is, you better preserve the inner product, otherwise we wouldn't call it a symmetry. And that is literally the definition of a unitary. Now it's a linear transformation, so it acts like that, right? If it, this is just a linear action. So it's just a linear unitary matrix, right? I'm not going to prove the theorem for you. I basically did. But it could also be an anti-unitary. What is an anti-unitary? Anti-unitary is defined by that line. You put in U and U dagger in the middle. It gives you identity, but also it gives you coupled conjugates, the result. That's an anti-unitary. Now, why is that allowed physically? Because the physics interpretation is not associated with inner products, it's associated with the norm of inner product. So if you had an anti-linear transformation, anti-unitary transformation representing your symmetry, you would have no physical way of understanding, understanding that it's not a symmetry, right? Because the only thing that's physically sensible is the probabilities, right? Good. So this is basically Wigner's theorem. It says that if you want to represent differential symmetries or symmetries in general on a Hilbert space, if you pick a representation, the representation vector space to be the Hilbert space, your transformations better be unitary or anti-unitary. Do you know any anti-unitary symmetry transformations? Time reversal. This is the example to have in mind. All right. We'll talk about that in detail. But now that I told you, you immediately realize that, oh, there is something subtle going on. The subtlety is with the fact that, well, if the vectors in the Hilbert space, if the vectors in the Hilbert space are rays, right? An overall phase multiplying all vectors is unphysical. So that means that if I want to talk about a representation of my group, do I need to care about the group multiplication? So what is the group multiplication? If U of G is the element of the group, and this is a unitary representation of it, we said that it should satisfy group multiplication. This is what it means. But if the overall thing is, I mean, these are only acting on kets from the left, ket and bras on the left and right, maybe I can just squeeze in some arbitrary phases, right? It would have no physical consequences, right? So I could modify the group multiplication, or not group multiplication. This is I modify my representation rule. I say a matrix U that was represented U of G that was G1 that was representing G1, multiply a matrix U of G2 representing the operation G2 gives me U of G1 G2 up to a phase that depends on G1 G2. Such a thing in mathematics is not a representation. Let's get that clear. By the definition of representation, this is not a representation, but it has a name. It's called a projective representation. In mathematics, mathematicians study projective representations for whatever reason they study it. For physicists, it's pretty clear why we study it, right? Because in vectors, in Hilbert space, we deal with rays. The overall phase is unphysical. Let's wait for this to sink. The only reason that, let me not say that. Yeah.
When you write the exponential,
yeah.
What's the data? I mean, how do you determine the phase that's caused?
Oh, I haven't told you how to determine it. I have a whole bunch of consistency conditions that I have to impose. But at this point, what I'm saying is that physics motivates me to talk about projective representations. And projective representation is a beast like that, right? Yeah.
In basic quantum mechanics, you do not care about the phase factor.
What do you mean? It's not.
I mean, the state, like, it preserves the norm of the state, right? So we don't care about what phase is sitting.
No, it has physical consequences. Well, let me give you one physics. Does anyone know a physics application of this? Like it's dramatic. It's absurdly dramatic. Like the simplest case of this. Does anyone have any simple example of this? What's that? No. What is a group that we have around us? Rotations, right? Rotation is a symmetry of nature. And I can pick my objects to transform my vector. I can pick rotation to act as a unitary on the Hilbert space. Or I can pick it to act as to be a projective representation. Do you guys know any consequence of that? What is the example you have in physics of a particle that when you go around by 2 pi, it doesn't come back to itself? Spinners. That's literally why spinners exist. That's literally why they exist. If we insist on representations and not projective representation, there would be no spinners in nature. Okay? So we'll come back to this. Any questions?
Can you find unitary or anti-unitary of all groups that you might use?
No. If we're exactly as you said, Wigner's theorem tells you that if you're talking about the representations in the Hilbert space, on the Hilbert space, it has to be unitary or anti-unitary. But if you're talking about some representation that's not Hilbert space, like these vectors, there's no reason for this to be unitary or anti-unitary.
Yeah, I'm handling the Hilbert space. But is this true for any Lie groups that we use? We can find unitary representation?
You're asking whether there exists.
Yeah,
every Lie group could be represented on Hilbert space?
On with unitary matrices.
Oh, does every group admit unitary representation? Oh, okay. Yes. I've not explained that. Correct. It does. As a matter of fact, your question is very interesting, actually. Let's instead of me coding theorems, let's go through examples and you will see. I'm tempted to say something, but okay, I'll hold on. I don't want to go on detours. But yeah, all the groups we talk about do admit unitary representations on the Hilbert space. Good. Any other questions? So when you're not talking about the Hilbert space, there's really no good reason to talk about, well, there's no particular reason to talk about unitary representations, right? For example, when you're talking about the action of Lorentz transformation on a field, it doesn't have to be unitary representation, right? Hopefully that's clear. As a matter of fact, it never is unitary. For those of you guys who know some group theory, but yeah. Good. All right, so let's talk Lie algebras, and I'm gonna give a little bit more detail. So the picture to have in mind, this is kind of cartoonish, but it's a good physical picture, is that here's your Lie group. Your Lie group is, for example, in this case, SON, right? Special orthogonal matrices that are n by n. This is a sphere topologically, right? And at each point, you have a tangent space, right? You have a tangent space at each point, and the number of the generators of that tangent space, linearly independent generators of the tangent space, is the dimension of the group, otherwise known as the dimension of the manifold, right? So that we're going to write it as dim G, right? Now take these tangent things, theta 1 to theta, schematically I write it as like a set of theta k's. Keep in mind that we're talking about the action of this on some vector space. So these are matrices. These theta 1 to theta k's. Well, sorry, no. I think my notation is a little bit different. These guys are elements. These guys are so. Well, depends how you want to do it. If I write this way, right? Theta 1 to theta n, so theta dim g. Actually, let me not comment on that. These are like analogs of g, right? Parameters. When we talk about the representation R of G, right? That is the matrix. Associates the matrix to that guy. Yeah, sorry, I think I jumped ahead of myself. All right. So now I'm writing U of G. Let me say I wish I had not done this. I don't think for anything I say in the next couple of slides, I do not need unitary representations. So when everywhere I've written U of theta, I mean R of theta, some representation, right? So I don't think that what I'm going to say, if I recall, none of what I'll say in the next couple of slides, I'll need unitary representation. So, all right, good. So here it is. The representation associates to some elements of the group are these vectors, right? Associates to each element of the group, some matrix. Now, when I multiply this matrix and that matrix, I should get another matrix. How do I calculate the resulting thing? Well, the way I should figure it out is that this should be U of some f of theta prime. Right? I have to have a way of calculating f of theta and theta prime. Right? Okay, so in particular, well, how do I want to say? Yeah, in particular, if I take the theta to be only in the k direction and theta prime to be only in the L direction, I should calculate an object like this. I think there's an extra L label here. Do I want to do it that way? Well, okay, sorry. That's all right. Let me not get distracted by that. All right, so first thing is, what you would like to do is you would like U of 0 to be represented by identity map, right? Which immediately tells you that f of theta and 0 better be theta, right? So f of theta and 0 is theta k. If f of theta k and 0 is theta k. Similarly, f of 0 and theta prime k is going to be theta prime k. So you know by linearity that you at least have these two terms as a linear piece. Now, what about the higher order terms? So the linear order terms is fixed by the requirement that U of 0 is the higher order term, let's just give it a coefficient, f of KLM. All right. So now my representation matrices expanded around identity, right? As I expand here, is identity plus I, theta k, lambda k. These are the matrices these are the Lie algebra generators, right? These are the Lie algebra generators. So I have a Lie algebra generator, but at the second order, there will be another matrix, lambda hat of k and L, that at this point, the only thing I know about this guy is that it must be symmetric in its indices. Right? Let's wait here and see if it sinks in. Right? I'm basically expanding the exponential, but I haven't derived the exponential for you yet. I'm just saying that there is a matrix. So you see, the group is continuous. Maybe I should have said this. The representation would also be continuous. So when I do a small deformation in the group, I can expand my representation in small parameters. That's what I'm doing here, right? identity is the zero piece. The first order piece, the coefficient of those, I'm going to identify as the generators of the Lie algebra. I told you that these are the vectors in the tangent space. In principle, at the next order, I have something else, lambda hat. So we'll see that this must be related to lambdas. This will be fixed. So I don't need a new matrix. For now, all we see is that it should be symmetric. Is it clear why it should be symmetric? Just by symmetry. Swap theta and theta prime. Okay.
One question, sorry.
Yeah.
How does the fact that u of theta k times u of 0 is equal to u of theta k induces the form of f?
Sorry, say it again.
I mean, you say that the
what is u of 0? Okay. That just means that f of theta and 0 is theta. F of theta k and 0 is f of theta k. And 0 must be theta k. Right?
Yeah.
And vice versa. F of 0 theta prime k has to be theta prime k.
And the second order term is just
at this point, I just put something. Right? Now, what do I have left? Well, very good. Now, I have to check that the composition works out, right? Meaning that I can plug this in here, here, and here, and expand to the second order. I have to make sure that all my coefficients work out nicely. That gives me a relation of this type. It tells me that this second order object cannot be a brand new object. It has to be lambda k, lambda L. It has to be second order in lambda k, but there could be a linear piece in it. I'm not doing this, but like it's something that I encourage you to do. There is no magic in here. I'm just taking this expansion, plugging into the matrix multiplication. So let me repeat exactly what I'm saying. So this is your F, plug it in here, right? And then take this expansion, plug it in use, and expand to a second order. You will find this. Good. So what do you learn? What do you learn immediately from this? Well, maybe you don't see it. We'll get there. All right. Well, this is what you learn immediately. Because this guy was symmetric, you could use the symmetry of this to write an expression for the commutator of the generators of the Lie algebra. And this is the structure of it, the structure that you find. This is just a consequence of these relations. And then CMKL is just basically the antisymmetry, F of LKM antisymmetrized in the lower indices. Right? These CKLMs are called the structure constants. They describe the Lie group and the Lie algebra. They're the data of the Lie group and Lie algebra. They're independent of the representation. I didn't tell you what the representation is, right? What does it mean to say what the representation is? It's giving you a set of matrices lambda hat k's and lambda hat l's that satisfy those commutation relations, right? I haven't given you that, but I'm saying that no matter what matrix is represented, this Lie algebra will hold. So these CKLMs are the data of the Lie algebra, right? It's very elegant. It's super elegant that you basically say that my Lie group and Lie algebra, all that structure is all in this stat, this coefficient. This is independent of the dimensionality or the representation. The dimensionality of the group matters, but not the representation. Good. Now, what happens if CKLMs are all zero? the Lie algebra is abelian. What is the Lie group? Abelian, right? So you learn immediately that all the non-trivial stuff are in the non-abelianness, right? The commutator of these guys. By the way, maybe it's not clear to you guys. This is exactly why in physics we talk about the commutators. Where does your story of quantum mechanics? What's the first commutator you saw in quantum mechanics? XMP, right? I imagine. X hat. Right? Why were we talking about this? Because if you exponentiate hat, this is a translation operator. If you exponentiate this guy, that's a shift in the momentum. So we're dealing with a bunch of symmetries of the field, right? In particular, translation symmetry in quantum mechanics, that representation, right? And we talked about the Lie algebra of it without ever mentioning those words. I'm hiding some subtleties here in the direct, right? There's a lot of this, but it says, but I'm just trying to show you that structure. I teach quantum mechanics earlier in the morning, and over there we just, it's really cute. You derive the fact that there has to be a P operator associated to translate. All you start with is just translation invariance, and you drive all these relations. This is really nice. Sectorize, no magic, but anyway. All right, good. So when the structure constants are zero, the Lie group is abelian, is commutative. And UG1, UG2 is UG2, UG1. What's an example of such an abelian group? Oh, if you have written it down. U1 or RD comma 1. Or RM comma N, or I don't know. Okay. These are translations in space, for example, space-time. Now, all right, so that's so far what we know. We know that these structure constants are related to the this FKLMs, but anti-symmetrized. Can we do better? Oddly, we still have one more independent relation. It's kind of funny. I don't have the intuition to tell you why this relation, but this is a new relation. U of theta prime times U of minus theta prime, U of minus theta has to be identical. Right? Hopefully that's clear. Now, if you expand this using the expressions you had, you're going to find this relation. This should hold for all FKLMs, lambda Ks, and theta and theta primes. From this, you conclude that FMLK has to be anti-symmetric in the LK components. The symmetrized part has to vanish. Right? So if I take FMLK, I can symmetrize that, and I can look at the anti-symmetrized part, or I can look at the symmetrized part. This guy vanishes. So the whole thing is anti-symmetric. This is all we've got. Right? So this way, I don't need to talk about two objects. I don't need to talk about CKLMs and FKLMs. There's only structure constants. They're the same, up to a factor of half or something. Right? So in this whole analysis, these constants appear over here were already the structure constants. Good? Any questions? From this, now it follows, if I go back here, look at this. The fact that this is anti-symmetric and this is symmetric tells you that this guy is really nothing but the symmetrized version of lambda and k. So you learn that this operator is not brand new. It's just the second order symmetrized sum multiplication of those two guys. This is what allows you to write the next magical relation, which is the group, the representation is of the Lie group is the exponential of the representation of the Lie algebra. This is a magical relation. All right, I have lied a little bit. Can anyone say where I've lied? When I said the structure constants are independent of the representation, let me call this C. What do you notice about this? Could this be uniquely defined? If not, why? What is the freedom left in these equations? Yeah. Where? Where would you put the face? What, like, how would you change things? Very good. Very, very, very good. Beautiful. So you could multiply these guys by minus ones. And that looks like we'll apply a minus one here, because this side is second order and this side is one. Turns out that this is something you could absorb in your redefinitions. It's not a crucial thing. However, if you multiply each of these guys with i's, right? You're gonna end up with an extra an extra I here. Now that matters. Why does that matter? Anyone? Very good. Very good. If I want a unitary representation, if u of theta is unitary, what is lambda k? Hermitian. If I put an I here, right, it's no longer Hermitian, it's anti-Hermitian. Well, yeah, it is anti-Hermitian. Right? So there is some sort of an I business here, room for some, and that's related to the type of representation that you're looking at. This is just a comment. 1 second. This is a comment because if you look at the structure constant, sometimes you see people take out i's, sometimes they do not take out i's. And that has to do with their thinking in advance, whether they're going to build their unitary representation or not. Yeah.
So can you get up 1 feet of the presentation?
Good.
And can you go down a little bit, please?
I haven't explained this part yet, but
Shouldn't it? I mean, it's something that I'm confused why the equation that equals to 0, why does it imply the symmetric part vanishes?
why does this imply that it must be symmetric?
No, the symmetric part vanishes.
Why does this imply that the symmetric part vanishes? Let's see. So what I'm gonna do is because I think what you could do is this. Let's see.
Shouldn't the indices of the thetas be swapped? On the
Yeah, maybe I have a typo here. Wait a second. Do I have a typo? No, it's about the theta prime you pick. Let me recall actually I worked. So if you pick oh yeah, actually. Yeah, good. So if you pick, let's see. Yeah, okay, sorry. I think I have a typo here. Thanks so much for pointing this out. I'll fix that next time. There's a typo. But actually, if you want to know where the typo is, just expand this equation. I did it way too fast. Let's expand this equation, and then you'll find where the typo is. Any other questions? All right. So here is a list. On the these are the Lie groups that you'll probably ever, these are the compact Lie groups that you'll probably ever, all of them they probably ever deal with unless you do very fancy stuff. UN that has n squared generators, right? Is that pretty wide? Well, you can just count it, right? Like unitary, the number of independent elements in n by n complex vector unitary matrices is n squared, and the generators are Hermitian, right? SUN has n squared minus 1, and the generators are traceless Hermitian. Is that part clear? Why traceless Hermitian? Think U2 and SU2. What are the generators of U2? Sigma X, sigma Y, sigma Z, Pauli matrices. What's the other one? Identity. What is the role of the identity? All the other three are traceless. Identity adds trace, right? This is in the exponent. When you exponentiate, it gives you some non-zero determinant. That S, it gives you e to a phase, the extra phase, right? So SUN, this is very important. SUN, the generators of SUN are all traceless Hermitian. This has a dramatic consequence for physics as well. We'll see that. ON is the generators are antisymmetric, n times n minus 1 over 2. Do you recall what the generators are? The Lie algebra of the ON. Yeah, the rotation generators, right? So y or minus y dot x. No, plus y dot x. Minus would be plus. All right. SON is has n times. Wait a second. There's a typo there. There's this one is plus. Is that right? No, wrong. They have the same number of parameters. Sorry about that. That was a silly mistake. So they both have n times n minus 1 over 2. What's the difference? One of them has 2 disconnected ones. And SPN, does anyone know what SPN is? No? No one has heard of SPN? Sorry? No. So it's in the same spirit that we've been talking about, right? So it's about what matrices, what inner product does it keep fixed, right? So we talked about, let's say, this kind of inner product. This gave us O, for example, if you have 2 negative 2 and minus 2, for instance. We talked about the inner product in the Hilbert space giving the U's, right? What is SP? Let's work in 2 dimensions. Let's talk about 2 dimensions. Oh, -1. It's the thing that keeps this invariant. This is not an inner product. Where have you seen this in physics? There's somewhere extremely. It's very crucial in physics. There's one place in the theory that's like super crucial. No. Volume of the phase space. So symplectic. The symplectic bilinear is the thing that allows you to associate volume to phase space. And the set of transformations that preserve the volume of the phase space, you all know about them, symplectic morphisms, they correspond to dynamics in classical physics, right? These are the matrices that preserve this are SPN. I think I'm making a mistake. It should be called SP2N. I forget the notation. Is it called SPN or SP2N? I think it's called SP2N. But yeah, these are called symplectomorphism, linear symplectomorphism, because this is the symplectic bilinear. Those are fancy words, math words for the phase space volume. Do you guys recall what is the Hamiltonian dynamics should keep the phase space volume in phase? No. Okay, that's a crucial result in classical physics.
You will see them?
Sorry?
You will see them?
Liouville theorem, yeah. By the way, actually, can anyone tell me what the Liouville theorem said? I'm going to write Liouville's theorem in very suggestive form. Does it look like something you recognize? So, yeah, I intentionally wrote this row. What this is a classical state, which is a probability distribution on the phase space. The time evolution of the classical state, the probability distribution in the phase space, is the Poisson bracket of the probability distribution with the Hamiltonian. How does this relation change in quantum mechanics? What's a quantum state? A density matrix. Here, and this becomes a quantum. Heisenberg equation. Anyway, so that's a different thing. Symplectomorphisms in quantum world have also a name. Oh my god, you guys recognize this? I'll be so impressed if some of you did. They're called linear Bogoliubov transformations. Anyway, I'm going to tangent, but we're going to run out of time, so let's go back. All right, good. So summary, let's review the Lie algebras. I'm at the end of the previous lecture now. So what is a Lie group? Lie group is a Lie group. It's a continuous differentiable group that I didn't define, but like I gave you a whole bunch of examples. We talk about these representations, R of G. This math track, this funky font is my way of trying to represent the Lie algebra. And of course, it has a representation, right? The representations of the Lie algebra and representations of the Lie group go hand in hand. As a matter of fact, let me just summarize for you. If you want to understand, the way we understand the representation theory of Lie groups is through the representation theory of their corresponding Lie algebras. This is how the whole idea pans out. Don't quote me on that. I'm not a mathematician. Maybe something to dimensional Lie group is an exception to everything you've ever seen. But, okay, so the way that these representations are related is that the Lie group representation is the exponentiated version of the Lie algebra representation, right? So Baker, Hausdorff, Campbell tells you how to multiply two exponents and write it in terms of the commutator of the exponents. What does that tell you? It tells you how to reconstruct group multiplications from the commutation relations of the Lie algebra. So it goes between the two. It only holds for finite dimensional Lie groups. All right. So the Lie algebra is like this. These are the structure constants. Example, we're gonna go through that. I don't need to say it. Oh, another thing. Sorry, I should have said this. I forgot to mention. I said that minus sign is arbitrary, but you can also complain about just like multiplying be generated by constant. Nobody complained about that, right? Multiplying by constant, of course, shift changes your structure constant by constant, structure constants by constant, right? But that's silly. What we usually do is we normalize our generators canonically using relations of this type. There are normalization conventions that often we take, right? We pick, for example, the trace, we fix the trace of these guys, right? You'll see that it's important every time you quote something about the structure constants and stuff, you use the canonical normalization of the generators. Good? All right. We also said that Wigner's theorem tells you that symmetries are represented as unitary and anti-unitary representation on the Hilbert space. That's what is symmetry is in the quantum world. All right. Any questions? Now, in the remaining 20 minutes or 25 minutes, I'm going to talk about representations of a group. Does anyone know why am I walking you through so much representation? Huh?
It allows you to say that there are eight.
Masochism.
Sorry,
No, I promise that I'll define for you what a particle is. So I'm on my way to define the particle, the field, right? I said it has to be an emergent concept, and that's the goal. So, any questions? Now we're going to talk about comparing representations. This is also very, very important. Two representations, R1 and R2, of the same group are equivalent if they are related by change of basis. What does that mean? Those are physicists talking. That's a physicist talking. What it means is that there exists an isometry such that for all G in the group, V R1 of G, V dagger is R2 of G. Do you see why this transformation is good? Does this transformation preserve group multiplication? How? R of what they call it G2, right? This becomes V R of G1, V dagger, V R of G2, V dagger. If this is to be a representation, this should be equal to R of G1, sorry, G2, G2 prime, which is V R of G1, G1 prime. Yeah. How do I get these two to be equal? If this is identical, right? What is the name of an operator that satisfies this relation? V. What's the name of an operator V such that V dagger V is identity? Isometry. Isometry. What is it missing to be unitary? Sorry? That's another way of saying it, but there's another way of saying it. Sorry? Well, this is a unit. This is a unitary. This is an isometry. This is a co-isometry. In finite dimensions, all isometries are unitaries. All co-isometries are unitary. So that's why you probably don't distinguish between them. However, in harmonic oscillator, can you tell me what's an isometry that's not a unitary? Think about that. That's a very simple example. Once it's infinite dimensional, there's a zoo of it. So is this relation clear? Yeah. If these are fine dimensional representation, then this is a unitary. We're good. A representation is called reducible if it can be made block diagonal by a change of basis, meaning that a representation is reducible if it is unitarily or isometrically, let's call unitarily for now, but equivalent to a block diagonal representation. If I have a representation R of G1, I have a representation R of G2, well, sorry, R1 of G and R2 of G, direct summing them clearly is representation, right? Hopefully that's clear. So if your representation is unitarily equivalent to that, then you have it's called a reducible representation. So you can see a representation that cannot be written in this way is called, actually, technically, it's called indecomposable. But for the purpose of this course, indecomposable is also irreducible. So irreducible, there are irreducible representations. You don't distinguish. So irreducible representations are the building for this course are the building blocks of all representations. Why? Because there is, as usual in classification, there's a result in math that says in many important groups. Actually, let me just cross this. I don't think I need any of this stuff. The theorem says finite dimensional unitary representations of compact groups can always be decomposed in terms of irreducible representations. Good. Any representation that's unitary for a compact group can be decomposed into irreducible representation. Decomposed means up to unitary, but written as direct sum. Right? Therefore, irreps are the building blocks of all unitary representations. There's a very, sorry, this is really ugly looking. Sorry about that. There's, okay, let this think, and I give you one subtlety regarding this. This is a true statement, but I'll give you an important physical case where this is not true. Is this good? That's why we talk about irreps. Irrep is an irreducible representation. Yeah.
But for instance, if I have, I don't know, rotation.
Yeah.
So I have the corresponding matrix. Then how do we know if it is reducible? I mean.
Very good. How do you know it's reducible? Very good question. Does anyone know how? How do you, given a representation, how do you know that whether you could unitarily rotate it to some block diagonal form? All right, I'll tell you. I'll tell you in a bit. You don't know? Okay. All right. So there's some group theory that's like crucial in this business. All right. Is everything good? I just want to highlight something and move on. This is a theorem. It's finite dimensional. It's called Peter-Weil theorem, what I just written in this ugly form. Right? Finite dimensional, I want to highlight. Here are two statements. Any non-compact group. You know what non-compact group is, right? Like, give me an example of non-compact group. Well, there's something simpler. Right? No, they're all compact. R is non-compact. Right? You don't know what compact group is. Oh, wow. Okay, so I have to. I don't know if I'll have time to talk about that. But anyway, R is non-compact. Anything that runs to infinity is non-compact. Anything that loops around and comes back is compact, right? Sphere is compact. SON is compact. ON is compact. SOD comma 1 is not compact. Why? It has a name. Boost. Boost can run all the way to infinity. You don't loop around, right? What were the representation of the boost? Caution cinches. They keep going. Rotations are compact, cosine and sine. They keep looping back, right? If a group is non-unitary, it does not admit any finite dimensional unitary representations. This is a very crucial result. Therefore, once you're talking about non-compact groups, this goes out of the picture. All right, so this is not going to be terribly useful for Lorentz transformations. Yeah.
When you say unitary vectors are building blocks of all vectors, that's the same as when you take V1 half tensor V1 half to V0 plus what? V1, the composition of the.
Oh no, you're talking about no. You're talking about flash-Gordon coefficients and tensoring. No, I'm not tensoring a representation. This is just direct sums.
Okay.
Yeah. All right. Is that's like physically very, very distinct. I can tell you the physics of that one. Good. All right. So why so much group theory? Here's a quote by Sidney Coleman. Sidney, S-I or S-Y? I don't know. A person who's tired of group theory is tired of life. Field theory is an intrinsically many particle theory. In the presence of relativity, we argued Lorentz symmetry tells you that the notion of one particle is doomed, right? It has to go out of the picture. You can't have a theory of a single particle, right? So we talked about field. We've been discussing so much of it. So now, but once we have field theory, what the hell was a particle anyway to start with? You have to be able to explain it. So how do particles come into the picture? A particle is an irreducible representation of the Poincare group. End of the sentence. That's what it is. That's why I've been walking you guys through this. All right. A particle is an irreducible representation. A fundamental particle is an irreducible representation of the Poincare group. So that's why we're going to go through representations of the Poincare group. Does anyone know already in advance what labels an irreducible representation of a Poincare group? What labels irreducible representation of the Poincare group? What labels particles in relativistic physics? Mass squared, mass, spin, done. You already know the representation theory. M squared and S. Right? Those are the labels, but that comes out of the representation theory. Right? Who told you that a particle will have spin and mass squared? Representation theory of Poincare group told you that. And we'll go through that. Now, here I'm going to make a cryptic comment because it's on the spot. We talked about quantum field theory. We said it had, so field theory had three principles. Now I want to put the Q back in quantum field. Locality, symmetry, and now I said positivity of energy, it becomes positivity of Hamiltonian. All right? You know in advance, I haven't described this in detail, but you know that Hamiltonian is the conserved charge associated to which symmetry of nature? Time translation. That's a Lie group. What's that Lie group?
R1.
R1, right? So we know Hamiltonian should be represented as a Hermitian operator, right? Because it's a symmetry of nature, it should be unitary. We wrote the unitary as e to the power of I, the generator, aka Hamiltonian. Therefore, Hamiltonian has to be self-adjoint. Therefore, energies must be real. But no principle tells you energy has to be positive. It's a brand new principle of the quantum field. So we could talk about representations that are unitary, right? Their generators will be Hermitian operators, right? But we could restrict to positive unitary representation or positive representation. It's actually called positive representation. Positive representation is a setup where you generate the Lie algebra or the Lie group using a self-adjoint operator that on top of it is positive. So this is a principle. This is absolutely a crucial principle of quantum field theory. Yeah.
But I mean, it was at the end put by hand, right? Because
It's an axiom.
Just
Axioms are put by hand. Yeah. It's an axiom. There's no way to derive this. There's no way to derive this. This is just principle.
I mean, it's a principle that's being local. I mean, we have negative energy densities, or
That is not in contradiction with positive Hamiltonian. All right. Positivity of Hamiltonian is the principle of quantum field theory. And I described it mathematically, right? There's translations. Wigner's theorem tells us that as a matter, there's also, I haven't discussed that, but you for translations in time, you can't have projective representations. So you're stuck with regular representations. Hamiltonian is nicely defined. I'm pushing myself to the right. But anyway, Hamiltonian is a self-adjoint operator. We want to use your transformations. On top of it, if you want to do physics, take it to generatively possible. Let me make another comment. What is the distinction between space and time from the point of view of quantum mechanics? They both, translations in both are generated by unitary groups, right? R, translations, time translation. The distinction is translation in space are not positive representations. Translation in time are positive representations. Good? That's very important. There was no way to a priori like see this. Like it has to be an axiom of quantum field theory or quantum mechanics for that matter. A negative means minus a positive operator. You mean a non-positive operator?
what exactly defines a positive operator?
Oh, it's a self-adjoint operator. It has a spectrum. The spectrum belongs to R plus.
Sorry, you said that.
Sorry.
Yeah.
Can anyone give me another definition of a positive operator? Give me two other definitions. Two other definitions that are cool. These are very important. If an operator is positive, right? One way of saying is that it's a self-adjoint operator. Let's start with self-adjoint operators, right? The spectrum is in R plus. That's positive. Can anyone give me another definition? That's a positive operator. It is a positive operator for every operator like this. I thought this in quantum mechanics like a little earlier this morning. This is always a positive operator. Not only this is always a positive operator, but also every positive operator can be always written this way for arbitrary cube. Also, this is also a positive operator. A positive operator is an operator is positive if and only if for all the vectors in the Hilbert space this relation holds. All right. Okay, that's enough for this. Yeah.
But if you say that negative energy densities are consistent with positivity, then how does it?
We're talking Hamiltonians. Hamiltonian energy density are two different things.
So,
Hamiltonian energy density are two different things.
so that doesn't make the positivity of negative density.
You mean negative energy density? Mass and energy density are two different things. Yeah, no, there's absolutely no contradictions. Hamiltonian quantum field theory is positive. It's an axiom. Yeah. Oh, of course. Of course. You would be penalized pretty darn bad. But what I would try to, okay, I'm going on tangents. You guys are pushing. I decided to add a new section to the course, which is about algebraic approach to quantum field theory. It's not true Lagrangians, right? It's about more like stuff that was developed in the 70s. Over there, I'll give you a more intuitive way of thinking about this. It has very, very dramatic consequences. As a matter of fact, this is the positivity of Hamiltonian is what we struggle with when we try to generalize quantum field theory to arbitrary spacetimes. That is what the struggle is. And then there's these algebraic methods identify a replacement for this principle. It was a huge part. It was like, yeah, it is a a beautiful area of research. It's mathematically pretty heavy, but yeah. Can anyone actually guess what does positivity do for us? If I have a positive operator, what does it do for us? It's hard. I don't know. You guys should know this. What is good about positive operators? What is special about this operator if H is positive? Yeah, no, but that's fine. So does e to the power of px. If this is positive, I can send t to t plus ip for positive. Right? So I can analytically continue t to the complex plane, upper half plane. That's how I get thermal physics. I get a lot of interesting physics out of this. That's all relying on this value. We can't do that otherwise. The whole connection to fine temperature physics is lost if Hamilton is not positive. All right, that's enough. Any other questions? I want to go through at least a couple of examples. Okay. I'm just going to go through one example. Questions? All right, so this is a very, very important example. I'll do only half of it. The other half, I'll make you guys do your homework. And I cannot stress this enough. You will not understand the Lorentz group if you don't work out this example. You will not understand spinors if you don't understand this. This is the simpler, way simpler case for a more complicated setup. But spinners, you better invest some time in it. First time it clicks, you're good, instead of like coming back to it and realizing you didn't understand it well. Okay, so we're going to start with a very, very important group in physics called SU2. The part that I won't have time to do is to compare it with another very, very important group in physics called SO3. They're both Lie algebras. One of them is a real Lie algebra. The other one is complex. What is the dimensionality of them? SU2, what's the dimensionality of the Lie group? 3. What's the dimensionality of SO3? 3. If I look at the tangent spaces of them, I can identify the tangent spaces. So the two groups are locally identical. Right? The two groups are locally identical. SO3 had, okay, hold on a second. So the Lie algebras are isomorphic, but the two groups are different. This is the origin of spinors in physics, right? The mismatch between SU2 and SO3. Does anyone know how they're related? Actually, can anyone say it right away? Sorry? I can't hear. Double cover. Yeah, so yeah, one of them, SU2 is twice as much. And yeah, okay, so that's we'll talk about covering spaces and double covers and things like that. And that double covered number 2 has to do with the possibility of having a minus sign as you go around by 2 pi. That allows you to define a fermion and nothing else. Bosons and fermions, that's all you got. Yeah. All right. So SU2, this SU2 means Lie algebra of SU2. By the way, you will notice that I'll play a weird trick. You'll see. I'm gonna abuse notation, and hopefully you can catch it. But I don't know. Maybe you don't catch it. It's all right. So the Lie algebra of SU2 has 3 generators. It's 3-dimensional. J1, J2, J3. They satisfy these relations, right? These are the structure constants. What are the structure constants? This is just the antisymmetric tensor, right? Epsilon ijk. All right, so I'm not going to prove this for you guys, but unitary irreducible representations of SU2 are labeled by quantum numbers S, called spin. It's a half integer, right? This is something they could just forget about physics, do mathematics and representation theory. If people came up with these representations. So I'm discussing unitary irreducible representations otherwise known as the building blocks of all the representations of SU2, finite dimensional representation, unitary representation, right? So if you have a Hilbert space somewhere where SU2 acts on it, it better be a direct sum of some of these guys I'm going to describe, right? You have a fancy Hilbert space in a garage somewhere hidden. If there's SU2 acting on it, it must act this way. And if there is a particle, it would have to transform as an irreducible of that. All right. So the irreducible are labeled by this half integer called spin. It's just a label. And the corresponding representation, the represented irreducible, irrep, that corresponds to spin S, has dimensionality 2s plus 1. Right? That's the dimensionality of it. These are matrices, UJIs, and these matrices are 2s plus 1 times 2s plus 1 dimensional. All right? So I'm going to go over it very quickly. There's a trivial irreducible representation when S is 0. Right? This is UJI's identity. All of the elements of the group are mapped to identity. Good? All right. This is a trivial representation. It always exists. Always one dimension. So if somebody asks if there's a every Lie group has admits a user representation, so yes, it does. Then there's a spin half irrep, which is so spin half. What's the dimensionality of the representation? 2s plus 1 is 2, right? So it's a two-dimensional representation, 2 by 2 complex matrices. What are they? These are the Pauli matrices, right? There are 3 of them. What if I had U2 instead of SU2? I'll have 4. What would be the fourth one? Identity. That's the block sphere expansion of density matrices that you could order. Spin half is called fundamental representation because it acts on a two-dimensional vector space, 2D Hilbert space. Why is it called fundamental? What was the definition of SU2? It was the thing that was preserving the inner product of a two-dimensional Hilbert space. Here we're representing as acting on the same damn Hilbert space. That's why it's called fundamental. I'm not defining for you mathematically what the fundamental representation is. Just describe it. Right? So what is the definition of SU2? The set of matrices U that preserve the inner product of the two-dimensional Hilbert space. Right? So if it preserves the inner product, that will act on. Therefore, what the form that it acts on is called a fundamental representation, and this is what it is. Right? Oh wow. Okay, I'm out of time, but I'll quickly wrap this up. Spin 1 representation is what dimensional? 3-dimensional. It has this form. They're again given by epsilon ijk's, and they look like this. Right? So I don't know if staring at them is useful, but do you guys recognize these matrices? Have you seen them? Sorry? Yeah, they're related to exactly. So there's another 3-dimensional representation that you might have seen, and these two are unitorial equivalent. So I leave it to you guys to think about what is the Lie algebra of SO3 and how are SU2 and SO3 related. I can give you a hint. Should I give you a hint? No, maybe not. All right. No, let me give you a hint. Don't look this up, okay? Just try to do it yourself because it is a helpful exercise. The hint is this: an arbitrary SU2 matrix is being written this way. Hopefully, I'll get this right. Minus. Yeah, minus. With the condition that alpha squared plus beta squared is 1. All right. This is an arbitrary SU2 matrix. You can easily convince yourself as SU2. All right. If you want to know how it relates to SO, or do not SO2, do not look it up. Just do it. Write these complex numbers this way in terms of some real four parameters, and this relation becomes x squared plus b squared plus c squared plus d squared equal to 1. And then I leave the rest to you guys to figure out how to relate these to Euler angles and these transformations. It's a very, very helpful exercise to do. All right, I'm out of time. Sorry about that. I didn't get to talk about simple Lie groups, but all right. So let me summarize. Give me 1 minute to summarize. What did we go? What did we talk about? Yeah, we talked about Lie groups and the algebras and all of that. You guys know that. Thank you so much.
You mentioned one thing,
Yes.
the unit 3